The quantification of discharge, whether it be during flood flow or environmental low flow conditions, is based upon the continuity equation. Discharge, Q, is in fact calculated in rivers at any one given instance in time rather than measured. The product of field measured in-stream velocities, here identified as V, and the related flowing cross-sectional attributes, identified as A, at a given location yield a discrete discharge observation. The discharge equation can be represented as the product of the average velocity, here denoted as V bar, and the flowing cross-sectional area at the given instance in time, whereby V bar simplifies all the spatial variations in the velocity field into one single representative value. However, in determining discharge, rather than, for instance, estimating the parameter such as in a modeling or probabilistic application, its quantification must recognize the spatial variability of the channel's bathymetry, morphology, bed material, and submergent vegetation, which can generate spatial differences in the velocity field and cross-sectional attributes at any one given location. Accurate field quantification of discharge is here achieved by discretizing the channel into a series of subsections, denoted here as vertical panels at each location, and measurements of flow depth, distance between panels, and velocities made at each discretized or panel location. Here we identify the common convention for referencing river measurements coinciding with the principal direction of flow occurring in a downstream direction, here into the screen. Therefore, the frame of reference is in a downstream facing direction, and river left and right are as denoted on the figure. What follows are discrete discharges being calculated proximal to each vertical panel, denoted here as small qi, which are determined from the product of now vertically averaged velocities at each panel, denoted here as V bar I, and the flowing cross-sectional area, shown here as A sub I, proximal to each vertical panel. Then, after the calculation of each discrete discharge Qi is calculated, they are summed to produce the total discharge of the flowing cross-sectional area. It is worth noting that at least one velocity Vi must be obtained at each panel location. However, the number and relative positions of velocities can increase, which can arise from the complexity of the flow field, bathymetry, and depth of water. There are different techniques in solving for the discrete flowing cross-sectional areas AI, which we will define subsequently in the demonstration. A few general techniques should be followed in selecting a location to undertake the velocity area method. In particular, if repeated measurements are intended, such as in the case of developing a stage discharge curve, or also known as a rating curve. Such cross-sectional locations are referred to as attestation measurements. The cross-section location should be away from obstructions such as beaver dams, debris jams, or boulder clusters, and conform as best as possible to the natural cross-sectional shape of the channel, both upstream and downstream. Avoid highly turbulent regions to reduce the potential of velocity bursts during the velocity measurements. Measurements should be taken in relatively straight sections of the channel, typically between bends such as on riffles or runs, where more parallel flow line assumptions and hydrostatic conditions of the water surface can be more readily made. For the given cross-section of interest, it should be divided up into approximately 25 to 30 subsections or verticals. Less panels can be used if the cross-section is relatively uniform. As long as one roughly maintains the recommended number of subsections, the choice in the specific spacing is commonly based upon the convenience of the measurement by the user. For instance, spacings of 0.5, 1, 2, or 5 meter intervals are easy values to enumerate and follow during the field measurement process, rather than multiples, for instance, 0.63 or 11.29, for example. Conversely, more panels may be needed if the bathymetry of the channel or the velocity field of the flowing cross-sectional area is visibly and/or experientially greater in complexity. Common guidelines to follow include: no subsection of the panel should contain more than approximately 10% of the total flow. This is a visual estimate. If this is the case, more panels should be added in these regions of notably higher velocities to further discretize the velocity field. Also, if there are notable changes in bathymetry, such as ledges, for example, or steep changes in channel bed slope, additional panels should be added to characterize both the channel bed bathymetry and the associated variations in velocities. When measuring velocities at discrete panel locations, if the flow depth is less than 0.75 meters, commonly a single discrete velocity measurement is adequate and made at the 0.6 depth measurement location to represent the average flow velocity. If the flow depth is greater than 0.75 meters, commonly two discrete velocities are measured per panel at the 2/10 and 8/10 depths to represent the average flow velocity. It is here noted that the locations of depth measurements are in reference to the water surface. However, from a field measurement perspective, they are measured from the stream bed, as the method is easier to execute. It is further worth noting that additional velocity measurements can be undertaken at each panel location to improve the representation of each average vertical panel velocity estimate. However, there are always resource trade-offs in increasing resolution. Now let's go to the field and implement the velocity area technique. Before we begin, and if you have not already done so, please watch the River Wading Safety Guidelines video so that we ensure that all persons of the field campaign are aware of the hazards and precautions that should be undertaken in these types of field endeavors. The first step is to span the tape measure across the channel. It is known that the tape measure does not need to start or end at the water's edge. For convenience, here, the tape measure spans further on both sides of the channel than the water's edge and is secured into the ground with metal pins at both ends. The tape measure is pulled taut so it does not sag and add additional length to the top width measurement of the channel. It should also be established at a convenient height that is above the water surface and not too high so that it is visually referenceable during field measurements. The position where the water intersects the ground surface on both sides of the cross-section, referred to as water's edge left and right, needs to be recorded. Here, water's edge at the left side of the channel in the video was noted to be at 0.61 meters and the right bank as 16.33 meters. This resulted in a total flowing top width of 15.72 meters. Also, from the first wading across the cross-section, it was noted that the channel was relatively uniform with no significant spatial variations in water surface velocities nor bathymetries, suggesting that the channel could be discretized evenly without the need for additional panels to be added in more concentrated flow or topographic locations. The flowing top width of the cross-section, 15.72 meters, was divided up into 20 panels, which yielded a spacing of 0.79 meters. This would have been an inconvenient number to maintain and keep track of over the course of the field measurements. To find a more convenient spacing value, the flowing top width was divided up into 25 panels, which yielded a spacing of 0.63 meters, also an inconvenient value to keep track of during field measurements. However, it was noted that 0.63 meters was close to 0.61 meters, which is a metric conversion of 2 feet. So flipping over the tape to the imperial side of the tape measure, 2-foot intervals were chosen for convenience for the frequency of measurement. The imperial units were then subsequently converted back to SI units in the post-processing. Here, by way of example, the technician chose a spacing interval that was convenient to keep track of in the field to reduce application error. Although this resulted in 26 vertical panels along the cross-section, there is nothing wrong with increasing the number of panels measured above 25 to 30 if it improves the accuracy and decreases user error. Finally, prior to undertaking the field velocity measurements, an explanation of the functioning of the topset measurement rod is merited. There are various versions of this rod depending upon the flow meter or sensor being used, however the application is generally the same. The topset rod is used to specify the depth or depths from the bed of the channel at the given panel location that the velocity measurements are made at. This device is employed when wading in streams is possible and safe to do so. If, however, flow depths are too deep for wading, this measurement device is abandoned and measurements may be taken from bridges or tethered velocity profilers. The base of the larger diameter rod, known as the depth gauge rod, rests on the stream bed at the desired location along a given cross-section. A second smaller rod, known as the sliding rod, is connected to the depth gauge rod via guides. The base of the sliding rod is furnished with a mount upon which the desired flow meter or sensor is secured. Finally, the topset reference location is the location where flow depths are measured from, and in the event that velocities are only being obtained at the 6/10 depth location, the depth of the velocity observations can be set without any additional calculations. Different flow meters or sensors can also be affixed to the topset rod. Shown here, the swaffer is a flow meter which rotates about a horizontal axis and is pointed into the direction of flow. These types of flow meters are rugged, can be relatively inexpensive, and typically range between 2 to 5% in measurement error. Another common type of horizontally mounted flow meter is the meter. One particular drawback of these types of meters is that if they are not oriented optimally into the dominant direction of the flow field, or if more complex 3D flow fields exist, they can produce notable errors in the measured versus true velocities. It is noted that this bias can be partially overcome by adding a directional fin on the lee of the meter to better hone the meter into the principal direction of flow. Vertically axis mounted meters, such as the price meter as shown here, are commonly more accurate than the horizontally axis mounted meters, ranging between 0.5 and 6% in error of measured velocities over true velocities. Their accuracy is the poorest at shallow flow conditions, but improves in accuracy in higher flow fields, which would commonly be associated with flood flow conditions. This type of meter functions similar to a wind anemometer, with the cups, referred to here as buckets for measurement of the velocity field, not being required to be perfectly aligned into the predominant flow field direction to capture the velocity field. This is a notable advantage as it removes some of the bias from the field person undertaking the measurements. One drawback of these flow meters is that they are often prone to blockages between the buckets and the main housing due to debris which often coincides with flood flow conditions. Stationary mounted sensors, whether they be electrical such as the Marsh-McBurney or Doppler sensors such as the Sontec flow tracker as shown here, have the advantage of no moving parts, which eliminates many concerns about fouled measurements due to debris, and they maintain a higher level of accuracy, typically between 1 and 2% of measured versus true velocities relative to mechanical meters. It is noted that these types of sensors must be calibrated to salinity conditions, in particular for the Marsh-McBurney, where the velocities are based upon the difference in the electrical resistance between an emitter and a receiver sensor. Velocities can be overestimated in highly saline waters. Calibration of velocities in a still bucket of water, sampled directly from the watercourse, is always recommended before proceeding with the desired measurements. Doppler-based flow meters do not in fact measure the velocities of the water proper, but rather the suspended particulate matter within the flow field, which is assumed to be moving at the microscale under the same magnitude and direction as the flowing water as it passes the sensor. There can be situations where velocities cannot be measured in ultra-pure water, such as in flumes. This challenge is easily overcome by seeding the water with very fine-grained particulate matter that remains in suspension. Usually this is not of concern for field application conditions. These next-generation flow meters, such as the Sontec flow tracker, also have onboard data loggers, which aid in the determination of panel locations and depths of velocity measurement on the fly, which further improve the accuracy in measurement of the velocity flow field and the resulting calculation of discharge. Here we will demonstrate the use of the topset rod. Focusing in on the upper portion of the topset rod, it is shown that the depth gauge rod is divided up into 5 centimeter intervals, shown here at the second hash mark at 10 centimeters. This is the rod that is used to measure the total flow depth. The hash marks on the sliding rod are scaled to interval distances of 40% of the depth gauge rod. Therefore, as shown here, the second hash mark on the depth gauge rod is transferred to the second hash mark on the sliding rod. This is a measured distance of 4 centimeters as shown on the tape measure. Intentionally, the sliding rod coincides with the application of the 6/10 velocity measurement depth rule. Thus, the velocity to be measured representing the average vertical velocity occurs at the location 60% below the water surface of the total measured flow depth, or, from a more convenient field measurement perspective, 40% above the stream bed surface. The use of the topset rod is demonstrated here using a staff gauge, which is merely a graduated meter plate with a depth of 0 coinciding with the base of the stream bed and the values increasing upward, which would coincide with the increasing stage of a river. A flow depth of 30 centimeters is shown. When the flow meter sits at the bottom of the rod, the top of the sliding rod rests at the topset reference location. The sliding rod is raised to the water surface, in other words, until the center line of the flow meter axis corresponds with the water surface. The depth of flow is then measured from the very top of the depth gauge rod. Here, counting down the hatches 5, 10, 15, 20, 25, and 30. This corresponds then to the observed 30 centimeter flow depth. Now, the same number of hatches are counted down on the sliding rod 5, 10, 15, 20, 25, and 30. The bottom of the piece of yellow tape here is used to identify this location. Then the sliding rod is moved down such that the base of the yellow tape rests at the top set rod reference location. It is now noted on the staff gauge that the depth from the base of the rod to the center line of the flow meter axis coincides with 12 centimeters, or 40% of the original 30 centimeter flow depth. Let's repeat this process for another flow depth, in this case 27 centimeters. First, the sliding rod is adjusted until the center line of the flowing meter axis coincides with the water surface. The number of hatches are counted down from the top of the large diameter depth gauge rod, 5, 10, 15, 20, 25, and proportionally a bit more, which is the estimate to 27 centimeters. The depth is called out to the second field person to be recorded. The number of hatches are then counted down on the sliding rod, 5, 10, 15, 20, 25, and proportionally a bit more to get to 27. The bottom of the yellow tape here denotes the proportional position on the sliding rod. The sliding rod is now adjusted such that the base of the yellow tape coincides with the top of the top set reference position. It is now noted on the staff gauge that the depth from the base of the rod to the center line of the flow meter axis corresponds with approximately 11 centimeters, or approximately 40% of the original 27 centimeter flow depth, 10.8 centimeters to be exact. Let's return to the field and employ the velocity area method. The end of the tape measure, which is affixed to the bank, is recorded at 0 feet. The left edge of water is observed at 2 feet and is intentionally assigned a total depth of 0 meters and a velocity of 0 meters per second. The edge of water left bank is recorded in the description column. The first open water measurement is taken at the 4-foot station, or referred to here as the cumulative change along the tape measure. The total flow depth measurement is transferred to the sliding rod and the flow meter elevation adjusted to the 60% elevation below the water surface, which is the same location as 40% of the total flow depth above the stream bed. To save on data recording, the specific depth of the velocity measurement is not recorded, as it is assumed that the topset rod is measuring the velocities at 40% above the stream bed. The velocity measurement control panel is set to the display averaging selection by turning the knob, and the average velocity recorded after 30 seconds of velocity monitoring. At this particular vertical location, a detectable velocity was not measured, although there was sufficient depth to acquire a measurement. Hence, the velocity here was insufficient to generate the minimum force required to spin the velocity impeller. So here, the velocity is assigned the code ND, which denotes that no detectable velocity was measured. In fact, there are 3 special codes that are used during the velocity area method, being ND for no detectable velocity observed, TS for a vertical velocity location where the flow depth is insufficient for the velocity meter to be used, or ISL, which is to identify the presence of an island at a single or multiple vertical panel locations. This is more common in larger rivers where an island or shoal may be present, being above the water surface at low flow but submerged at high flow conditions. The codes ND and TS are used in the post-processing of the data to apply different velocity interpolation procedures in assigning velocities to the unmeasurable panel locations. Measurements proceed onwards across the cross-section at 2-foot spacing towards the right bank of the channel. The cumulative change, total flow depth, and time average measured velocities at depths 40% above the stream bed are measured at each vertical panel location and called out to the second field person to be recorded. We see as the field hydrologist nears the right bank of the channel, the flow depths become very shallow. Here at the 50-foot location, the flow depth is just under 2 centimeters and the flow meter is not fully submerged in the water column. Here the flow velocity is recorded with the code TS, indicating that there was insufficient flow depth present to obtain a measurement. Finally, the water's edge at the right bank of the cross-section is recorded at 50 feet 7 inches and is noted in the description column, concluding this part of the field measurement campaign. In part 2 of this video, we will post-process the data and apply different techniques to calculate panel discharges and the resulting total flow. In addition, we'll also explore alternative velocity representations and demonstrate how a field calculated discharge contributes to a rating curve.